In the last several lecture videos, we've been reviewing one-way analysis of variance for the purpose of establishing a conceptual framework in preparation for studies of hierarchical linear models. We continue looking at the one-way ANOVA model, but in this video, we consider it from a somewhat different perspective. Previously, we considered the treatments used in the experiment to be the only treatments of interest to the researcher and about which the researcher would like to draw inferences. Now we consider the treatments to be a random sample from a population of treatments, and it is this entire population of treatments that is of interest to the researcher and about which the researcher would like to draw inferences. This change in how we view the treatments used in the experiment impacts how we interpret the model and also how we interpret the results of the ANOVA. In addition, it provides a very important link to the kinds of models that we will be looking at in the context of hierarchical linear modeling. Here's an outline of what we'll be looking at in this video. We'll first define and differentiate between fixed effects and random effects. We will review the one-way fixed effects model and then introduce the one-way random effects model. We will then see how to perform the ANOVA for the one-way random effects model. Once we've done that, we'll look at how to estimate the variance components in the one-way random effects model. We'll see how to construct point estimates as well as confidence interval estimates for those variance components. So let's jump in. The first thing we need to do is to define and differentiate between fixed effects and random effects. And so let's review fixed effects. If the treatments used in the experiment constitute all of the treatments of interest to the researcher, then the effects of those treatments are constants, also known as fixed effects, in the statistical model. The focus of hypothesis tests involving the treatments will be to determine whether differences exist in the means of the fixed populations. That is, whether any of the fixed effects of the treatments are non-zero. The focus of estimation involving the treatments will be on estimating the means of the fixed populations and differences between them. That is, estimating the fixed treatment effects and differences between them. Here are some examples of fixed treatment effects. An extension researcher selects 3 particular varieties of corn to use in an on-farm field trial. The purpose is to determine whether any of the varieties is the best on that farm. No other varieties of corn are of interest to the extension researcher and the farm owner. In this context, corn variety is a fixed effect. Another example would be a plant manager who is interested in comparing the productivity of the plant's 5 machine operators in using a new machine. There are currently no other operators employed by the plant, so these are the only operators of interest to the manager. In this particular context, operator is a fixed effect. Next, let's define random effects. If the treatments used in the experiment are a random sample of treatments from a larger population of treatments that is of interest to the researcher, then the effects of those treatments are random variables, also called random effects, in the statistical model. The inference space will be the population of all treatments, and the focus of hypothesis tests will be to determine whether variation exists among the means of all treatments in the population, not just the treatments in the sample. The focus of estimation will be on estimating the variability among all treatments in the population. Here are some examples of random treatment effects. An extension researcher randomly selects 3 varieties of corn from a larger population of corn varieties to use in a field trial. The researcher is interested in drawing inferences that apply across the entire population of corn varieties. In this context, corn variety is a random effect. As another example, a plant has purchased a new automated machine, and the plant manager is interested in determining whether variation exists in productivity using this machine among the plant's machine operators. The plant has 100 machine operators, too many to involve all of them in an experiment. So the plant manager randomly selects 5 machine operators to participate in the study. The manager is interested in drawing inferences that apply to the entire population of all 100 machine operators employed by this plant. In this context, operator is a random effect. Now let's review the one-way fixed effects model. The statistical model for the one-way fixed effects treatment structure in a completely randomized design structure can be written in the following way. Y sub ij equal to u sub I plus epsilon sub ij, where I goes from 1 to t being the number of treatments, and j going from 1 up to n sub I, where n sub I is the number of experimental units receiving the ith treatment. Y sub ij is the measured response on the jth experimental unit receiving treatment I. Mu sub I is the population mean response under treatment I. And epsilon sub ij is the random error associated with the jth experimental unit receiving treatment I. This is the means model representation for the one-way fixed effects model. The one-way fixed effects model can also be expressed as an effects model as follows. Y sub ij equal to mu plus alpha sub I plus epsilon sub ij, where y sub ij is again the measured response on the jth experimental unit receiving treatment I. Mu is the arithmetic mean of the treatment means, so it's equal to 1 over t times the sum I going from 1 to t of the mu sub i's. Alpha sub I is the fixed effect of treatment I, where alpha sub I is equal to the difference mu sub I minus mu, and therefore the sum of the alpha sub i's is equal to 0. And finally, epsilon sub ij is the random error associated with the jth experimental unit receiving treatment I. The random error terms, the epsilon sub ij's, are random variables with mean 0 and variance sigma squared for all I and j. The epsilon sub ij's are assumed to be stochastically independent within and across treatment groups. In addition, for purposes of inference, it is usually assumed that the epsilon sub ij's are normally distributed. Now note that because we have not subscripted sigma squared with either I or j, there is an implicit assumption here that the error terms have the same variance for all treatment groups. Now let's identify the parameters in the one-way fixed effects model. For the means model representation, we have the treatment means, mu1, mu2, and so forth up to mu sub t. And so we have t parameters there. We also have the error variance, sigma squared, which is an additional parameter. And so in the means model representation, we have t plus 1 parameters. In the effects model representation, we have the overall mean, u. So that's a parameter. We have the treatment effects, the alpha sub i's. Now notice that since the alpha sub i's by definition sum to 0, there are only t minus 1 linearly independent treatment effects in the model. And so there are t minus 1 parameters here. And then finally we have the error variance, sigma squared. That is one parameter. And so in the effects model representation, we also have t plus 1 parameters. Now let's introduce the one-way random effects model. The statistical model for the one-way random effects treatment structure in a completely randomized design structure is given by y sub ij equal to mu sub I plus epsilon sub ij, where I goes from 1 to t and j goes from 1 to n sub I. Again, y sub I is the measured response on the jth experimental unit receiving treatment I, but in this model, mu sub I is the population mean of the ith randomly selected treatment from the population of treatments. And finally, epsilon sub ij is the random error associated with the jth experimental unit receiving treatment I. This representation of the one-way random effects model is called the means model representation. We can also represent the one-way random effects model as an effects model. In this case, we have y sub ij equal to mu plus alpha sub I plus epsilon sub ij, where again y sub ij is the measured response on the jth experimental unit receiving treatment I. Mu is the mean of all treatment means across the entire population of treatments, and so that is a constant. Alpha sub I is the effect of the ith randomly selected treatment from the population of treatments, and so alpha sub I is in this case a random variable. And finally, epsilon sub ij is the random error associated with the jth experimental unit receiving treatment I. Now, in the means model representation, the mu sub i's are random variables with mean mu and variance that we will denote by sigma squared sub tau. The mu sub i's are assumed to be stochastically independent, and in addition, for the purposes of inference, it is assumed that the mu sub i's are normally distributed. In the effects model representation, the alpha sub i's are random variables with mean 0 and variance sigma squared sub tau. The alpha sub i's are assumed to be stochastically independent. In addition, for the purposes of inference, it is assumed that the alpha sub i's are normally distributed. The error terms, the epsilon sub ij's, are random variables with mean 0 and variance sigma squared for all I and j. The epsilon sub ij's are assumed to be stochastically independent within and across treatment groups, and in addition, for purposes of inference, it is assumed that the error terms are normally distributed. Now, one other assumption in the random effects model is that the random effects, whether they're represented as mu sub i's or alpha sub i's, are considered to be independent of the error terms. Next, let's identify the parameters in the one-way random effects model. In the means model representation, we have the overall mean, that's one parameter. We have the treatment variance, sigma squared sub tau, that's an additional parameter. And we have the error variance, sigma squared, one more parameter. And so in the means model representation, we have three parameters that need to be estimated. In the effects model representation, we again have the overall mean, mu, and so that's one parameter. We have the treatment variance, sigma squared sub tau, that's an additional parameter. And we have the error variance, one more parameter. And so in the effects model representation, we have three parameters as well. And so we can see here that regardless of how we represent this one-way random effects model, whether as a means model or as an effects model, we have three parameters, and in fact, they are the same three parameters that need to be estimated. Now let's look at how to perform the analysis of variance for the one-way random effects model. The calculations for the one-way random effects ANOVA are the same as they are for the one-way fixed effects ANOVA. Now that's great news, isn't it? Because we already know how to do the ANOVA for the one-way fixed effects model. And so that means we also know how to do the ANOVA for the one-way random effects model. However, the specific hypotheses being tested by the ANOVA F-test are different for the random effects model than they are for the fixed effects model. That's necessarily the case because the parameters in the random effects model are different than the parameters in the fixed effects model. Having said that, the question addressed by the ANOVA F-test for the one-way random effects model is similar to the question addressed by the ANOVA F-test for the one-way fixed effects model. There are some differences, however. First, the hypotheses are expressed in terms of different parameters. And again, this is necessarily the case because the parameters in the one-way random effects model are different than the parameters in the one-way fixed effects model. In addition, the inference for the random effects model ANOVA F-test is to a broader set of treatments than the inference based on the fixed effects model ANOVA F-test. This can be seen by looking at the expected mean squares for the two types of models. And so let's look at the expected mean squares for the one-way ANOVA model. Let's first look at the expected value of the MSE. Now, as we can see here, regardless of whether we're working with a fixed effects model or a random effects model, the expected value of the mean squared error, the MSE in the ANOVA table, is equal to sigma squared, the variance of the model error terms. Next, let's look at the expected value of the MST, the mean square for treatments. Now, if the model is a fixed effect model, then the expected value of MST is equal to sigma squared plus this expression involving the squared values of the alphas. On the other hand, if the model is a random effects model, then the expected value of MST is equal to sigma squared plus this quantity that involves sigma squared sub t, the variance of the treatments. Now, if we have equal replication, for example, R experimental units per treatment, then the expressions for the expected value of MST simplify a bit. In particular, if we have a fixed effects model, then the expected mean square for treatments is sigma squared plus R, the common sample size, times the sum of the squared alpha values divided by t minus 1. If the model is a random effects model, then the expected value of MST is sigma squared plus R times sigma squared sub tau. Now, how do we use this information? Well, recall that the F statistic for treatments is equal to the ratio of the mean square for treatments in the numerator to the mean squared error in the denominator. For the fixed effects model, from the expression for the expected value of the MST, we can see that the F statistic will follow the F distribution if and only if all of the treatment effects, that is, all of the alpha sub i's, are equal to 0. This implies that the null hypothesis being tested by the F statistic for the fixed effects model is that all of the alpha sub i's are equal to 0. The alternative is that at least one of those alpha sub i's is different than 0. Now, this is equivalent to the usual ANOVA hypotheses. The null hypothesis being that mu1, mu2, and so forth up to mu sub t are all equal. In other words, that there are no differences among the treatment means. The alternative would be the opposite of that, that at least one mean is different than the rest. Now for the random effects model, the F statistic will follow the F distribution if and only if the variance of the treatments, sigma squared sub tau, is equal to 0. And so this implies that the hypotheses being tested by the F statistic for the random effects model are as follows. The null hypothesis is that the variance of the treatments, sigma squared sub tau, is equal to 0, against the alternative hypothesis that the variance of the treatments across the entire population, sigma squared sub tau, is greater than 0. Now these hypotheses can be stated in words in the following way. The null hypothesis being that no differences exist among the treatment means across the entire population of treatments, against the alternative that says that differences do exist among the treatment means in the population of treatments. The rejection criteria of the ANOVA F test for the random effects model is the same as it is for the fixed effects model. In particular, for both types of models, the null hypothesis is rejected if and only if the F statistic is greater than the upper alpha percentage point of the F distribution with t-1 numerator degrees of freedom and n-t denominator degrees of freedom. Now, not only are the F-test hypotheses stated in terms of different parameters for the random effects model than they are for the fixed effects model, but the inference space, that is, the set of objects about which we can draw inferences, is different as well. In particular, the inference space for the ANOVA F test for the random effects model is broader than the inference space for the F test based on the fixed effects model. Specifically, the inference space for the fixed effects ANOVA F test involves only the set of treatments used in the experiment. On the other hand, the inference space for the random effects ANOVA F test is in relation to the entire population of treatments from which the treatments used in the experiment were selected. Next, we're going to look at estimation of the variance components in the one-way random effects model. Let's first look at estimation of the model error variance. We'll first obtain a point estimate. As was seen in the table of expected mean squares for the one-way random effects ANOVA, the expected value of the mean square for error, MSE, is equal to sigma squared. And so this implies that an unbiased estimator of sigma squared, the model error variance, is given by the MSE. And so we will denote this using our standard notation sigma hat squared. Next, let's look at confidence interval estimation of sigma squared. The first interval we look at is going to be based on the chi-square distribution. Now, in previous lecture videos, we saw how to construct confidence limits and a two-sided confidence interval for sigma squared based on the chi-square distribution in the context of a fixed effects model. The procedure is exactly the same in the context of a random effects model, and so I'm not going to duplicate that discussion here. I'll just refer you back to those previous lecture videos if you would like to review that. We can also construct approximate confidence intervals for sigma squared based on the normal distribution. And so here are the formulas for one-sided confidence limits and a two-sided confidence interval for sigma squared. And again, keep in mind that these are approximate confidence intervals in the sense that the confidence levels are approximate. Now, these intervals also are the same that we got in the context of the fixed effects model. And so I'll refer you back to those videos if you would like to review the development of and discussion about these particular intervals. Now let's look at how to estimate the treatment variance, sigma squared sub tau. We'll start off with point estimation. As was seen in the table of expected mean squares, the expected value of the mean square for treatments, MST, has the following form: sigma squared plus, and then the product of this expression involving the sample sizes, and sigma squared sub tau divided by t minus 1. From this, we can come up with an unbiased estimator of sigma squared sub tau. We're going to denote this estimator by sigma hat squared sub tau, and it's equal to the difference between the mean square for treatments and the mean squared error divided by this expression involving the sample sizes divided by t minus 1. If the treatments are equally replicated, that is, if n sub I is equal to r observations for each treatment, then the unbiased estimator for the random treatment variance, sigma squared sub tau, simplifies to this nicer expression. So sigma hat squared sub tau is equal to the difference between the mean square for treatments and the mean squared error divided by r, the common sample size. Next, we're going to see how to construct confidence interval estimates of sigma squared sub tau, and we'll look at two different methods. The first method is going to be based on the chi-square distribution. If the model assumptions are met, then the point estimator of the treatment variance has a chi-square distribution. The problem is that the degrees of freedom associated with that chi-square distribution are unknown. They can be approximated, however, and one common way to approximate the degrees of freedom is using Satterthwaite's approximation. The formula for Satterthwaite's approximate degrees of freedom is shown here, and we're going to denote these approximate degrees of freedom by V. The following slide gives one-sided and two-sided confidence intervals for sigma squared sub tau based on the chi-square distribution with the degrees of freedom approximated by V. Now, these confidence limits and the two-sided confidence interval have the same form as they have for the corresponding confidence limits and confidence interval for the error variance, sigma squared. The difference is that instead of having degrees of freedom for error in these formulas, we have the approximate degrees of freedom for sigma hat squared sub tau, which is V. And so that really is the only difference between these formulas and the formulas for the confidence intervals for sigma squared. We can also use the normal distribution to come up with approximate confidence intervals for sigma squared sub tau. These formulas are of the same form as the formulas that we came up with for estimating sigma squared, the differences being that they involve sigma hat squared sub tau instead of sigma hat squared, and also the degrees of freedom in these formulas are V, the approximate degrees of freedom associated with that point estimator, instead of the degrees of freedom for error. Let's summarize what we've done. We defined and differentiated between fixed effects and random effects. We reviewed the one-way fixed effects model, and then we introduced the one-way random effects model. We related the ANOVA procedure for the one-way random effects model to the ANOVA procedure for the one-way fixed effects model. We identified the hypotheses being tested by the ANOVA F-test for the one-way random effects model by looking at the expected mean squares. We then gave formulas for estimating the variance components in the one-way random effects model. We looked at point estimators, and we also constructed two types of confidence interval estimators, one based on the chi-square distribution and one based on the normal distribution. So that's what I wanted to show you in this lecture video. I'll see you in the next video.